So, welcome everyone. My name is Felipe, and I will be your host for today's webinar on dissecting real-world database performance dilemmas. So today I am in great company with both my fellow countrymen and my fellow countrywoman joining me today. And we have selected 4 real-life performance problems in production and how we address them with ScyllaDB. Before we get started, let's quickly understand what ScyllaDB is, and most importantly, why ScyllaDB. So, for those of you who are not familiar with ScyllaDB yet, it is the database behind Game Changers, organizations whose success depends upon delivering engaging experiences with impressive speed. ScyllaDB was built with a close-to-the-metal design that squeezes every possible ounce of performance out of modern infrastructure. This translates to predictable low latencies, even at high throughputs. And with such consistent innovation, the adoption of our database has grown to over 400 key players worldwide. So, some of you will recognize many of the companies which are being pictured here, such as Discord, for example, who's using ScyllaDB to connect millions of individuals all around the world in real time. Or Epic Games, who's using ScyllaDB behind the scenes for distribution of game engines behind Unreal Engine. So as we can see, ScyllaDB is used across many different industries and for entirely different types of use cases. Therefore, if you have a need for high throughput and predictable low latencies, do take your time to talk to us. We'll be more than happy to hear about your story and know how and whether we are able to assist. Quick intro about ourselves. So my name is Felipe, and I work as a solution architect at ScyllaDB. I frequently engage with users in our community in order to help teams and individuals to solve their most challenging performance problems. More recently, we have published our database performance at scale book, which I'm really proud to be one of the authors. And the book is a freely available publication. You can simply download. And basically, both Noeli and Guilherme were also contributors to this publication. And guys, thank you very much for all your contributions. Speaking of them, Noeli, hi, and would you please introduce yourself?
Hello guys, so I'm Noeli, technical support team leader at ScyllaDB. Always taking on new challenges, learning new things, and of course, striving to ensure the customer's satisfaction. Guilherme.
Thanks, Noeli. Yeah, Gui?
Thank you very much, team. I'm Guilherme Nogueira, Senior Solutions Architect here at ScyllaDB, and I have years of experience with Linux and general distributed systems. I'm always helping prospects successfully experiment a product, Scylla as a product, Scylla as a technology, and nicely ramp up when they become a customer. I also recently got a puppy, which I'm just about to show her. Can you advance the next slide? Yeah. So
yeah, puppy time.
This is Vanilla.
Oh
yeah, puppy time. This is Vanilla, Baunilha in Portuguese. And she's a very nice little girl. She's a Chihuahua breed, and she's just welcome to the family.
Oh my God, she's so cute. Well, welcome, Vanilla. And thank you so much for sharing that moment of your life with us. Gui, I mean, who doesn't love puppies, right? I mean, really nice. I love her already.
And I think that not often people that are attending to workshops and presentations will see such a cute puppy like that.
Exactly. I mean, so
nice
consider
surprise.
you guys should consider, yeah, you guys should consider yourselves lucky. So we have prepared a lot of surprises for you today. Awesome. Thanks, Gui. All right, cool. Let's move on through our agenda. I mean, I cannot take Vanilla out of my head now. It's your fault, Gui. So, as I have mentioned in the beginning, we selected 4 different real-life production stories involving performance problems, which all of us three were involved in. we definitely have a lot of content to run through today, so let's just go ahead and get started with the first one. So, hunting down a latency problem. And this was a very interesting one, which I was primarily involved in and required quite an investigation for us in order to get to the bottom of it. And it is one of those stories where you eventually realize how a single configuration option may inadvertently end up affecting your latencies in a really bad way. So, to give you guys some context, we had this, now a customer who was evaluating ScyllaDB for their real-time bidding use case. And they were very satisfied with the results when compared to DynamoDB, which is the database they were coming from. And initially, they had configured this 3-node cluster deployment, pretty much standard, and they have run a set of tests, and the results was that the latency was within the requirements, and we assisted them in tuning their drivers to follow all best practices, and they were really happy with all the results. All right, so far so good. I mean, everything was working nicely and it was performing really well until we have hit the problem. And what happened is that it turns out that the actual production deployment was a multi-region one. And during their tests, we have only tested their application within a single region. So in order to fulfill the requirement of going multi-region, we simply added a new data center to their ScyllaDB cluster. And what happened after was very interesting, to say the least. And as soon as the new region started serving traffic, we realized that their latencies went to the roof beyond their requirements. So in the monitoring metrics we are sharing, we can see their latencies spiking beyond 400 milliseconds until it eventually stabilizes, goes down, but remains at around 60 to 80 milliseconds. So this is definitely not the numbers we were expecting to see. So here's a question to you from the audience. How would you explain the problem, and what would be your follow-up steps in the problem determination? Do let us know what you think in the chat. But in the meantime, while we are waiting for you to think and write down your answers, let me ask Noeli what she thinks about it. So Noeli, any insights?
Yes, I would start by investigating if there is any kind of background operation, for example, repair, because sometimes what can happen is that if a repair is triggered after the second DC is added, I mean, we already would, at this point, we already have the key spaces replicated to the new data center. And in case a repair starts happening before rebuilding the new data center properly, I'm sure that this would impact the latency. So this is at first the first hunch where I would start investigating first.
Yeah, that's actually a very good feedback. So yeah, we add a new data center to your ScyllaDB cluster, data is not streamed automatically, right? And if repair runs, data will start being streamed from the primary region to the new one and this may end up affecting your latencies. Yes, that's a good way of investigation. Now let's see if you got it right. So a few more data points related to this issue. One of the things which caught my attention while evaluating their problem is that we noticed that their high P99 latencies were not coming from their application queries. So in order for us to understand that, you need to understand that ScyllaDB implements this concept of which we call as scheduling groups, where we completely isolate resources altogether. For example, queries coming from the application should have priority over other classes, such as compactions and repairs, which are background activities, as Noelle mentioned in her answer. What we can see in this slide, and I don't know if it's good for you guys to read, but don't worry, I'm going to explain it to you. What we can see is that the main class, the first one here, which is highlighted, which is used by ScyllaDB internal queries, was the main contributor to the perceived high latency, which is constantly above 50 milliseconds. In fact, when we look at the numbers, when we look at the latency numbers alone from this class, we realized that the P99 latency was driven by the network round trip time from one region to another. All right. So, so at this point, we already had a good suspect. But what exactly was running in this class for reaching out a separate data center? So what we did was we enabled tracing for some time and then collected the results. And the numbers in the screen, in particular, the red highlighted ones, reveal that most of the queries being run internally by the database were related to authentication. And the Cassandra user was the one running such kinds of queries. At this point, we understand why internal queries are affecting the client-side latencies, because authentication is taking too long to complete, as it has to always traverse to another region. But the question we should be asking is, why is authentication exhibiting this behavior? I mean, shouldn't it simply authenticate within the local region and just return back to the application, whether it was successful or not? So it turns out that in ScyllaDB, and also in Apache Cassandra for that matter, the Cassandra user is a special type of user, which is considered super administrator. And when you create a ScyllaDB cluster, in order to keep compatibility with Cassandra, we also create a Cassandra user. And to prevent you from potentially locking you off from the database should anything wrong happen, for example, if you change your password, but the changed password does not replicate to other replicas, to prevent you locking yourself, your access, all queries, whenever you're going to use the super user, all queries are done with a consistency level of quorum. And in a multi-data center setup, quorum queries will always traverse to other regions. Therefore, the fix here was quite simple. We simply created a different role for the application to use, and the problem was solved. And this is a really good example on how a specific setting may end up impacting your overall performance. All right, so the next story is Chicken Time Series Bomb, and this is a story Noelle brought to us, and she's now going to present. So Noelle, would you please amaze us?
Thank you, Felipe. Okay, so this is regarding a major streaming customer. And everything started when we received alerts of a download and history usage for this specific cluster because it was hosted in Scylla Cloud. Hence, it's managed by us from Scylla side. And what a big advantage, by the way, because then we from support could promptly start acting on it. So during the troubleshoot, we analyzed the logs, the monitoring to check the current situation. Okay, I'm trying to pass the slide, but for some reason I can't. Okay.
I think you got it. Yeah.
Thank you. So we could see that a repair was running, taking long to finish, and that it was impacting the latency. And why we can't point the repair? Because analyzing in a higher time window, the monitoring, we could see that the latencies were stable in other periods while the repair was not running. And another interesting symptom was that the compactions not being able to handle the rate of incoming files. So why is that happening? So what would be your guess at first? Any ideas?
While the chat adds some theories, I would certainly review the key space replication factor. You might have an imbalance on how replicas are distributed across the cluster, such as if you do have a replication factor of 1 and a very large partition, or large cell, large row, you could end up with a single node representing the whole storage for that table and that partition, and you would eventually get up with a lot of compactions increasing.
That's a good point of view. This is something that we could consider. So, no one tell the chat any guess? Would it be too hard to troubleshoot? Okay. Compactions, compaction options, compaction strats. All right. So
interesting.
Yeah. Okay. Right. So the compactions not being able to handle the rate of coming files. This is something. So this can be related to the data modeling. So then we reviewed the schema, placed it in this cluster, the key space, the tables, indeed the compaction strategy. Because trying to understand a bit more of the use case for this customer, they were making use of Jaeger as an integration, which was using a lot of tables. So 131 to be more precise. So we took some time to review them, but there was something in specific that caught us our attention, because since this was a time to live TTL case, we understand that a good compaction strategy for this is a time window. And then this is looking a bit further to the time window compaction strategy tables. We noticed something interesting about the compaction window set for these tables, and it was quite a lot, 55. And we can see that it was set for 1 hour. So 1 hour booked that translating, doing a basic math calculation, translating the TTL in seconds, that would mean 30 days. And considering that our tables was splitting in 1 hour bucket, what would translate to 720 windows and think that this is for a single table. Can't imagine for 55. So it was generating a huge number of open files. Felipe, can you explain a bit further regarding the time of compaction strategy window and why we should be careful while setting these the time for the bucket?
Of course. Thanks, Noeli. So under the hood, what time window compaction does, what the time window compaction strategy does under the hood is to essentially split your data into what we call time buckets as you define it when you create your table. Time window compaction strategy, as you explained it, is a great fit for time series types of workloads because all data within a specific time window gets compacted all together. And given that behavior, it makes very efficiently for the database to answer queries such as retrieve me the average within the past 7 days, or compute the sum of entries recorded within the last month. And the reason why those queries can be done in a very performant way is because all the database has to do is to traverse the time window buckets which have been created, which you defined when you created a table. That said, the problem with time window compaction strategy is when it is incorrectly used, as you have demonstrated. For example, you have shown us a time to live of 30 days. And the customer in this case, or the Jagger integration, decided to create time buckets of 1 hour only. If you were to run a query where you wanted to simply retrieve all data for whatever, a specific device or a specific log entry, I don't know what the customer is actually storing, the kind of data they're storing in the database. But anyway, if they were to retrieve data up to 30 days ago, the database would need to read from over 700 SS tables, right? And this is for a single table. When you sum that to the fact that the customer in question had several tables configured in the same way, we can then realize that this bottleneck, this will eventually become a bottleneck, which would basically prevent the customer from scaling any further. Does that help?
Yes, a lot. Thank you. Okay, so then what we did to try to solve the problem, right? Because then the repair completed, the memory utilization improved, and we could notice, try to change the slide. Okay, and as the post-event findings, we tried to understand better from the customer about their use case. Why were they using such a low bucket, generating such a high number of files? And then the customer explains that they didn't exactly created those tables. They were just integrating the Jaeger tool to Scylla, and then the Jaeger was responsible to create the tables accordingly. Then, in order to try to improve this and to help us in the future, we from Scylla side created a GitHub issue and case for Jaeger to explain them how would be the better setting for compaction strategy. And they even fixed that, by the way. So nowadays we wouldn't hit the same issue anymore. And also Felipe, our great guy that is presenting to you, introduced a nice tunable parameter in Scylla available the open source 5.2 and enterprise 2023.1. Would you like to talk a bit about your nice parameter, Felipe?
Not necessarily. I mean, the setting I developed is pretty much self-explainable. It's basically if you try to create a time window compaction strategy table with too many windows, the database will forbid you. We are essentially going to tell you in advance, hey, we are not going to create the table because we are not quite sure you know what you're doing. And of course, if you disagree with that statement and you believe you know what you're doing, then you can disable this check. Yeah.
Yes. Then what were the lessons learned from this? So be suspicious of activities taking a long time to complete because, for example, in this case was the repair, but there can be many other several cases like replacement of nodes, scaling resizing procedures, etc. Review how the third-party tools that you are integrating to the cluster work under the hood. And rest assured, if you need it, ScyllaCloud expertise will be around to back you up. So, because in this case, it was a good advantage that we could properly take a look at the cluster because the cluster was managed on our side by ScyllaCloud. And then we have full access to the cluster. We can troubleshoot it easily. We can collect the logs. We can expedite the investigation in this case. So I think it was everything that I had to share about this case. Let's move on. Felipe,
Let's move on.
Guilherme is going to present the next use case, right?
Yeah, next one is Gui. And but by the way, Noeli, thank you very much. That was very insightful. And so Gui is the one who actually brought up this story. And so Gui, break a leg and please buy some patch treats for vanilla. Okay? So go ahead.
Thank you, and for sure we'll do. So I'm going to review a fairly common scenario as a use case. This use case had several decades of user data being stored, and they needed to be retrieved live in a very fast response time. So they needed a live database for it all. It was a long-term Cassandra deployment, so it was running for a couple of years. It had massive data growth year on year and dozens of terabytes per cluster. So it's just a very naturally increasing and growing use case, and alongside growing with data and operations. And they had multiple clusters per geo. So they had some parts of the data set was replicated between Asia and Europe. They had some data that's been siloed per region, depending on the part of the use case. But in general, it was a massive 260 terabytes raw data set that was replicated across multiple clusters within those regions. And as I said before, this is being a Cassandra cluster, we should just move forward and scale it horizontally, right? Let me change the slide. Yep.
You got
so
it.
when you continue to scale horizontally a cluster, such as a Cassandra cluster, what you end up is with a node sprawl situation where you have multiple clusters scaling to keep up with the data growth. And you start with a very humble 9-node cluster, then scale up to 12, 18, 30, 90, and then get to 200, 400 nodes. So
Wow.
managing multiple clusters of hundreds of nodes is very challenging, not only from the technical perspective, but also from the cost perspective, because every new hardware that we input to this cluster has additional costs to keep running, and it has actual more a new point of failure introduced to your cluster. So in a 400 nodes cluster, you have 400 possible point of failures that you need to take care of and maintain and keep healthy. And if you consider that each node has CPU and RAM dedicated, then the sum of that is just stratospherical. Assuming that each one of them has 64 vCPUs and 12 gigs and 512 gigs of RAM. If you get 400 nodes, then it's 25K vCPUs and just over 2 terabytes of RAM. So that's a massive deployment, managing a lot of data and serving that in real time in a very scalable way. But I think that it begs the question, so what you should do next? So I would like to hear from the chat. If you were facing the situation where your use case is booming, you're growing, your company is doing well, you're amassed a massive amount of data, but you still have a lot of expectation to grow. How would you deal with the situation? How you would still keep up with this ever increasing data set? And meanwhile, the chat is responding. Felipe, I'd like to hear from you. What you would do in this situation?
I would be very happy of having this kind of problem, to be quite honest. You just said my use case is scaling like nonstop, which very likely means I am having revenue like nonstop, right? It's a good problem to think about. But yes, I mean, it's definitely a concern, because if at that scale, it essentially means that your use case is critical for people, right? So we cannot by any means afford any kind of outage. I think the most natural follow-up would be essentially to look for an alternative, right? So what should I do instead of just scaling like forever? And until I found that alternative, I mean, I would just keep up on scaling, because want it or not, the solution is currently working and I don't have an alternative. Make sense?
Yeah, no, that makes a lot of sense. And I think that while the chat has great input, I think that the look for alternative edge here is what currently drove that use case, that look into Scylla. So their current technology restricted them to larger, denser nodes that could sustain more storage per node. And it also did not make very efficient use of the hardware that it was running on. So you were basically wasting CPU and RAM on nodes just to store data, to serve very little requests per second across the whole global deployment. And at the same time, you were having to spend money on operations to keep the cluster running and healthy, and on infrastructure costs to keep all those hundreds and hundreds of nodes alive 24/7. Oops, sorry, I skipped one slide. So in this case, or in this edge, how can ScyllaDB help, and how ScyllaDB helped this customer? So if you consider the previous math, 64 vCPU, 400 nodes, that's 25K vCPUs in a single cluster. And then moving to Scylla, which is able to make use of very high dense storage within AWS, which are the i3 and 24x large instances, which are massively 60 terabytes of disk each with just 96 CPUs. So a 21 node cluster of that instance type was able to sustain that whole data set per region, and was still able to reduce the number of CPUs in 12 times. So from 25K vCPUs, we have now just 2K vCPUs, a much more efficient use of the hardware, and a very high reduction in node count, a 20 times node reduction, because you just have fewer nodes as point of failures within your cluster. So I think that is a really nice example of how Scylla as a technology can help customers moving from massive or ever-growing data sets, live, real-time data sets, and move that into a technology that makes a more efficient use of the hardware that it's running on. And I think that we have the last use case to present. Back to you, Felipe.
Yeah, thanks, Guy. I mean, and I think just one thing that maybe you forgot to mention is the fact that this is also a huge cost reduction, right? I mean, from 400 nodes to 21, I mean, this is truly impressive. Yeah. So thank you so much for that. So let's jump into our last one we prepared for you today. So hot facts code insights is basically a variation of the scenario Guy just presented. So let's see what it is all about. So a bit of context for us. we have been engaged by this feed aggregator company after they had suffered a major data loss involving their HBase deployment. So in case you are curious, no, I don't have details over what was the actual data loss, but I'm only reporting what they told us back at the time. In particular, they were previously they were running on-prem, and they had a huge storage footprint, which they were looking to store in ScyllaDB, as they basically could no longer rely in their previous solution. So as they were on-prem, they couldn't simply dispose their existing infrastructure they already had set up for HBase, and they stated that they would like a feature similar as tiered storage, that is, their frequently accessed data would need to be quickly retrieved by the database in very single-digit millisecond latencies, whereas their code data would be least accessed, yet still relevant to their users. So performance was important. It wasn't just as important as the hot data, but it was performance, the latency, the access latency was too important. On top of that, they also had no retention periods, meaning that data would be forever stored in their database, and as Guy mentioned, over time, over years and years, this is a deployment that inevitably will only grow and grow and grow, right? So some of the challenges. Their natural concern and doubts involved which strategies to employ in order to move data from one type of storage to another. For example, would it be best for them to have a single cluster with 2 data centers, each one for a particular group of data? Or would it be better for them to have separate deployments altogether and implement replication from hot to cold on their own? In that sense, if they decided to go in that direction, would it make sense for them to use CDC or simply dual write from their application? And most importantly, how to ensure that data gets removed from the hot deployment after the replication to the cold one is completed, and we no longer need that data sitting there in the cold, in the hot deployment. So I have shared a few of the strategies which the customer could implement, and I think for this particular story, what's ultimately important for us to understand is that there are no right or wrong answers in that case. In particular, there are trade-offs among each one of them. And my question to you, for you to post into the chat, therefore, is which strategy would you follow and why? And in the meantime, while we are waiting for your answers, Guy, what are your thoughts about some of them?
Sure. So one of the strategies that you mentioned is using dual writes. And I think that's one that is most natural because it's fairly technology independent. You can do dual writes with any kind of technology, but it also introduces a lot of noise. What I mean by that is your speed of a commit will be dictated by your lowest component. So let's say your hot, fast cluster can do an operation in half of a millisecond, while your cold cluster takes a full millisecond or even 2 milliseconds just to commit a single write due to the speed of the disks. So your whole operation will be dragged down to the speed limit of your highest latency component of this dual writes pattern, and you would then probably see some timeouts amassing, and your operations will basically be reduced to a crawl.
Very good. Thank you so much for your feedback. And it does make sense. I mean, that's general distributed systems theory, right? In a distributed system, the speed of your system is dictated by your slowest node. Yeah, good. Good call out. And by the way, guys, I'm loving all of your feedback in the chat. Thank you so much for participating, and keep it coming. I mean, we are here to basically interact with you. But all that said, I mean, if they have a need for cold storage, then why not just use object storage, right? Technologies such as Amazon S3 or Google Cloud Storage exist for years. They are really successful. So why do they would offload their code data to a database in the first place? That's a fair question. And we also wanted to understand the reasons behind it. First, remember that they were running on-prem rather than in the cloud. And second, they didn't really have the option to decommission their previous infrastructure used by Apache HBase. Local object storage technologies do exist, such as MinIO, for example, but according to their tests, they realized that its latencies were way beyond what they would expect. After all, want it or not, they still had to query the code data within acceptable thresholds. Finally, if they were to move to object storage, that would introduce cloud networking costs, plus the round trip time latency to traverse from their on-prem deployment to the cloud. And the complexity of implementing such a solution was yet another reason why they discarded that option. I mean, they would need to implement a mechanism to move from hot to cold anyway. So it eventually became redundant. Another important consideration when we are talking about managing hundreds of terabytes or even petabytes of data has to do with how much data can your database store. And the thing is, every database has a limit, and with ScyllaDB, this is no different. We also have a limit. In general, we recommend that you try to keep a 1 to 30 memory to storage ratio if your focus is lower latency for performance. And if you have a storage heavy use case where you want to store dense amounts of data, we recommend you do not exceed the ratio of 1 to 100. For example, if you assign 8 gigabytes of memory to a ScyllaDB node, then you could store up to 800 gigabytes of data in that node. Beyond that, it may happen that the database may suffer heavy memory pressure, and well, interesting things might start to happen. So ultimately, the customer decided to go with a single cluster deployment, where they would have a specific region for their hot data and another for their cold data. The replication strategy, the way to move data from hot to cold, the strategy they followed was the following. So first, the application primarily writes only to the hot data center with a local consistency level, thus ensuring lower latencies. The replication would asynchronously be done by ScyllaDB from one region to another, so that they wouldn't need to bother about replicating data on their own. But in order to evict the data from hot to cold, after some period of time, they would simply remove all replicas from the key space involved in the hot region, therefore making it only available within the hot one. And they actually explained the reason why they chose this path, which was because they already had employed similar mechanisms in HBase. So the switch would basically, for them at least, would involve zero friction. All right. So Let's summarize what we have discussed today. We have discussed and brought up plenty of insights for you. And here's a quick summary of what we've seen and learned. So first, an overlooked setting, such as the user you use to authenticate with against your database, may be the culprit for your performance problems. Then, Noelle showed us an interesting situation where an integration was incorrectly configuring compaction strategy settings, which eventually fired back. Guy explained how ensuring your database scales vertically and efficiently makes use of your underlying hardware can give you several benefits, exemplifying with how a Cassandra deployment comprised of hundreds of nodes could be reduced to a dozen in ScyllaDB. And lastly, we discussed replication strategy and how to split hot data from cold data. Again, in that particular story, there is no right or wrong approach to follow, and your decisions should be ultimately guided by the trade-offs involved in each one of the options we discussed. All right? And if you liked what we presented today, then you may find these and more performance-related insights in our database performance at Scale book. Remember, it is free to download, so all you have to do is to go to our website and grab your copy and enjoy reading it during your holidays. All right? So this brings us to the Q&A part of our session. Before we jump into questions, here are some resources for you to follow along. Register and start a free trial in ScyllaDB Cloud. Noelle, as she mentioned, she is one of the brilliant minds supporting it, and I'm sure she will be more than happy to assist you with. All right? Simply go to ScyllaDB.com/cloud in order to get started. Guilherme spoke a lot about ScyllaDB's ability to scale up and take the most out of your underlying infrastructure, resulting in cost savings and better performance. If you'd like to know more about how ScyllaDB works under the hood, how do we get to amazing performance numbers, and watch a performance-oriented demo, register for our workshop at ScyllaDB.com/events. Lastly, ScyllaDB Summit is around the corner, and registrations have already started. Next year, we are going to have an amazing lineup of organizations sharing their insights on how ScyllaDB is taking them to the next level. Disney Streaming, Expedia, Supercell are just a few of the already confirmed speakers for next year. Plus, of course, our own ScyllaDB engineering talks. We are going to also have ScyllaDB engineering talks around new features and improvements. So go to ScyllaDB.com/summit and save your seat. All right? So all that said, let's get started with our Q&A. And I'll be honest with you, it's the first time I am opening the Q&A to see all of your questions. Guys, Noelle or Gui, is there any questions you guys would like to tackle in the meantime? Okay, I see we have one. How ScyllaDB is different from other similar NoSQL databases? Gui, would you like to answer that one?
Yes, for sure. So how the primary difference is how Scylla interacts with the hardware and how well Scylla makes use of the available resources for each process. The design of Scylla is the same of Cassandra in the terms of data, so the same schemas and the same theories you would apply from Cassandra to Scylla, but the way that Scylla is implemented makes a very efficient use of the hardware with delivering a very low predictable low tail latency. So you would expect your read P99s to be extremely predictable. And if you're using the right set of technologies and the right set of parameters, usually we deliver a single digits milliseconds with a fair reduction in cost as well. So the major uptake in how Scylla interacts with the hardware, the great use of the hardware, and the predictable, low tail latency, and highest throughput, I think are the largest differentiators from Scylla from other NoSQL competitors.
Mm-hmm. Yeah, very, very good, Gui. Maybe let's see if Noeli knows the answer for that one. Is there a ScyllaDB API that can be used for integration with another application like Postgres has?
We have some APIs from Scylla, but to integrate with other. Yes, because for example, we have some APIs that we can export metrics. So it can be exported to another solution like Prometheus, Datadog. So if I'm correct, will be something like that.
Yeah, and I mean, it's not clear exactly what the question means by integrating with another application. For example, if you simply want to connect an application to the database, you use a driver, right, and then follow the protocol, which is either CQL or the DynamoDB protocol. We support both. But if you are actually mentioning about ScyllaDB management APIs, then yes, we do have some, which we expose in port 10,000, right? So you can send RESTful API commands to those ports, and then you can, shut down nodes, repair, compact, those kind of stuff, all right? Maybe another one for, let me see, who should I give this question to? Yeah, for Noeli again. If we were using the ScyllaDB open source version on our own infrastructure, is there a straightforward path to migrate to ScyllaDB Cloud in the future?
Yes, of course, it is possible. First of all, I would advise to talk to our solutions architect because they can help to review a better sizing for this. And then later, there is the possibility of some tools that we can use to migrate the data from the open source cluster to the Scylla Cloud cluster.
Good. Perfect. Yeah, and we also have the ScyllaDB migrator, right, which makes essentially migrating from one platform to the cloud fairly simple. Gui, tricky questions, two tricky questions. Does ScyllaDB has a C# driver, and does ScyllaDB support vectors or vector engine?
No, that's two great questions. So for the C# driver, we don't currently offer a native Scylla, although we do have Cassandra compatibility, API compatibility. So any driver that is fit to run against a Cassandra cluster will work on a ScyllaDB cluster. So you can use the community Apache Cassandra C# driver to communicate with Scylla. Although, as far as I heard, we're working on a shard-aware version of the C# driver for down the road. So there might be something in the next quarters. And with regards to supporting vectors or vector engines directly, ScyllaDB doesn't have the immediate support for it, but we do have a very nice and reported integration with Genus Graph, which is a graph integration layer that supports a flexible backend storage, such as Cassandra and Scylla. And you can use Scylla as a very good, fast, and performance backend for Genus Graph integration. So I would say that yes, combined with other open source projects within the community.
Yeah, perfect. Thanks, Gui. And I think the last one we are going to tackle today, because guys, we are going to follow up with you answering all of your questions. There are just many here. But the last question we are going to answer today is one related to how to contribute to ScyllaDB, because after all, ScyllaDB is open source, right? So if you guys would like to contribute to ScyllaDB, the main place you should be heading to is to github.com/ScyllaDB. And there you will find projects for pretty much everything, from C*, which is the core engine that powers ScyllaDB, the database itself. If you are familiar with Java, Go, then you can contribute to the drivers or our CDC drivers, etc. and so on, all right? So do take some time to visit our GitHub and get familiarized with it. And thank you very much for your contribution in advance. All right. So, guys, thank you so much for your great feedback into the chat. And unfortunately, we have to say goodbye because we want to be respectful with everyone's timing. So, Gui, Noeli, thank you so much for joining us today. Thank you very much, audience. And we wish you all a very great end of the year, and that you guys no longer have to face any performance problems in the coming year. All right? Guys, thank you so much, and talk to you next time. See ya.